So today we move to the quarterfinal number 4 of the 2025 MIT Integratin Bee. And the first problem in that quarterfinal was this integral from x equals to 0 to x equals to 10 of x squared with a small change in the fractional part or what I usually call the sawtooth function of x plus a half. And then problem number 2 is the integral from x equals to 0 to 1 of x squared over the square root of x times 1 minus x. And problem number 3 is the integral, indefinite integral of 1 over x to the 8 minus x to the 6. So very interesting problems, and I hope you stay put and really enjoy to see what we develop here. So let's try to re-express the d fractional part of x plus a half into a form that is easy to understand. So that can be expressed as the derivative of that fractional part of x plus a half with respect to x times dx. Now what is x plus a half fractional part? That is the same as x plus a half minus the integer part, and that is the floor or the floor function of x plus a half. So having the x and y axis as shown here, x plus a half is that function, that straight line with the gradient of 1 and the intercept of a half here, positive half. And so looking at this floor function, you have the integer part, from negative a half to positive a half, you have it being 0, and then from positive a half to 1.5, you have it at 1, and so on and so on and so on and so on and so on, such that the difference between x plus a half and the floor function really becomes this sawtooth-like function. So you have it increase from 0 all the way up to 1, then it drops down at that transition point of x equals to a half, x equals to 1.5, x equals to 2.5, x equals to 3.5, all the way to x equals to 10.5. But our integral only stops at 10 here. So what is the derivative? The derivative of this sawtooth function, or the derivative of the fractional part of x plus a half, is you have this line of gradient 1, but then when x equals to k and a half, and let's say at these points here, what you see is the gradient is a negative infinity in a way, because the change is negative 1, but it's within a delta x or 0. So that is what we are faced with at the moment. Okay, and so we're going to deal with that and insert this negative infinity for when we are at these transition points, but otherwise it's just 1. So let's see how we can incorporate that. So what we're going to do here is we are going to say, okay, this derivative here that we've created is 1 when x is not equal to k minus a half, and k spans from 1 up to 10, right? And so what happens is we're going to have two separate integrals, that is from x equals to 0 to x equals to 10. This just collapses to 1. But again, we're going to have a summation. And here we now have a delta Dirac function that allows us now to say that it's negative of that delta Dirac function times the x squared, because the gradient here all of a sudden balloons to infinity within that instantaneous value. But when we integrate across that function, and then we're going to just get this value squared. Then we sum it, because those instantaneous changes in this gradient show up at the 10 different positions. So we're going to sum it, and this negative comes out, and then the delta Dirac function allows us to just now be able to square the specific values of x. So this is easy. So x cubed over 3 from x equals to 0 to 10 minus square this is k squared minus k plus a quarter. And since we have this simple summation from k equal to 1 to 10, so this is from k equal to 1 to n, k squared is, when you sum it, it comes to n times n plus 1 times 2n plus 1 over 6. And then k is simply n times n plus 1 over 2. So using this, we're going to be able to solve for this summation. So for k squared, we said it's n times n plus 1 times 2n plus 1 over 6, which is n being 10 is 10 times 11 times 21 over 6 minus n times n plus 1 over 2, that is 10 times 11 over 2, plus a quarter 10 times, so 10 times a quarter. So this is the same as 1000 over 3 minus 385 plus 55 minus 5 over 2. And that becomes 2000 over 6, obviously. 2000 minus 1980 minus 15. Having said the common denominator is 6, and that is 2000 minus 1980 is 20. 20 minus 15 is 5. 5 over 6 happens to be our answer. The problem number 2, my quick inclination here is substitute for x, with x being equal to sine squared u. And so dx du equals to 2 sine u cosine u. And so you can substitute for dx with 2 sine u cosine u du. Now, when x equals to 0, 0 equals to sine squared u, square root of 0 is 0, and so u is equals to arc sine of 0, which is 0. And then when x equals to 1, square root of 1 is positive 1. Arc sine of 1 is going to be equal to pi over 2. So let's just go in and substitute everything. So the limits, as shown here, x sine squared u, and then sine squared u squared here in the numerator because sine squared, sine to the power 4u, and then dx becomes 2 sine u cosine u. So 1 minus sine squared u is cosine squared u, and we keep going. So that means that the denominator here becomes sine u cosine u, which obviously would cancel with what we have in the numerator here. And then, so this would cancel, and we can pull the 2 out. So you have 2 times the integral from x equals to 0 to pi over 2 of sine to the power sine to the power 4u. And so that sine to the power 4u is the same as sine squared u times sine squared u. Which means that now we can integrate sine squared u being expressed as 1 minus cosine 2u over 2. This is a relationship, but when you square that, we get a quarter pulled out, and we have 1 minus 2 cosine u plus cosine squared 2u. Cosine squared 2u can be expressed further as a half of 1 plus cosine 4u. So this is a simple integral, because now this becomes 1/2 plus 1 here becomes 3 over 2 minus 2 cosine 2u plus a half cosine 4u, which can be integrated as 2 over 4 3 over 2u minus 2 over 2 sine u plus a half sine 4u, with limit 0 and upper limit pi over 2. So since this is a continuous function, so we'll just substitute the limits as shown here, and so we have 3 over 2 pi over 2 times pi over 2 minus 0. Obviously the 2 over 4 constant is out here, and then here minus 2 over 2 sine pi, 2 times pi over 2 is going to be pi minus sine 0. So sine pi is going to be 0, sine 0 is 0, 8. Sine 4u, that's sine 4 times pi over 2 is going to be sine 2 pi minus sine 0. Sine 2 pi is 0, sine 0 is 0, so this passes 0. And so we're just going to be left with 2 over 4 times 3 over 2 times pi over 2. So these 2's cancel, so we have 3 over 4 times pi over 2, which is going to be 3 over 8 times pi. And that's the answer that was being sought for. So this is a cool problem. And one thing I would like to do is just pull out the x to the 6th in the denominator, so you have left with x squared minus 1. So x squared minus 1 is the same as x minus 1 times x plus 1, the difference of two squares. So that becomes now indefinite integral of half, expressing this 1 over x minus 1 times x plus 1 into partial fractions, becomes half x 1 over x minus 1 minus 1 over x plus 1. And so from here, we're going to, in a stepwise fashion, link in x from the x to the power 6, one at a time, until all the 6 x's disappear. So let's begin by that. So we have half the integral of 1 over x to the 5th, open bracket, 1 over x times x minus 1 minus 1 over x times x plus 1. Okay, and that becomes this part here, 1 over x times x minus 1 is the same as 1 over x minus 1 minus 1 over x minus 1 minus, open bracket, this here becomes 1 over x minus 1 over x plus 1. And as you can see, we have negative 1 over x minus 1 over x. So this binds together, becomes 2 over x. And then this minus minus here means that we have a plus 1 over x. So we can re-express that as half the integral of 1 over x to the 5th, open bracket, 1 over x minus 1 plus 1 over x plus 1 minus 2 over x. Then again, we link 1x into the bracket. So we have 1 over 2 integral of 1 over x to the 4th, open bracket, times, open bracket, 1 over x times x minus 1 plus 1 over x times x plus 1 minus 2x squared. So this becomes, this part here becomes 1 over x minus 1 minus 1 over x plus this, open brackets, 1 over x minus 1 over x plus 1. So you see this plus and this minus means that we can pull this minus out here, and this 1 over x plus 1, this negative 1 over x plus 1 over x, they cancel each other. So we're left with the half times the indefinite integral of 1 over x to the fourth, 1 over x minus 1 minus 1 over x plus 1 minus 2 over x squared. Then we leak another x into, so we have here half the integral of x to the power 3, open bracket, 1 over x times x minus 1 minus 1 over x times x plus 1 minus 2x to the power 3. So we again continue with the process, and we do that, and this process continues until eventually we do have a an expression that can now be integrated independently. So the final expression here is we have 1 over x minus 1 minus 1 over x plus 1 minus 2x squared minus 2x to the fourth minus 2x to the power 6, which can be integrated as half the natural logarithm of x minus 1 minus half natural logarithm of x plus 1, and the half and the 2 here cancel, so we have 1 over x. This integrated, we have plus 1 over 3x cubed plus here this integrated times the half here for plus 1 over 5 times x to the power 5 plus the integration constant. Now using the rules of logarithm, we can combine these two here so that we have half x minus 1 over x plus 1 natural log plus 1 over x plus 1 over 3x cubed plus 1 over 5x to the power 5 plus the integration constant. And that is the answer that was being sought for. And that brings us to the end of quarterfinals number 4. We do beseech you and encourage you to subscribe to our channel if you haven't subscribed. Please do like our video if you do appreciate the work that is ongoing. And if you have colleagues that would like to also learn more about integration in calculus, please do share this video to them. Until next time, bye bye and have a blessed evening or a blessed morning.